Good afternoon, students. In the last video, I attempted to do Coulomb's law of charges and the law of superposition, which turned out to be really long. So I'm going to make another go at this and sort of shorten it up into two different lessons. And in the first lesson, we're just going to talk about Coulomb's law and do some basic kinds of problems. And in the second part of the lesson, which will be on a separate little video, we're going to do the law of superposition and charges in a plane. So let's get started. Back around 1785, a guy named Charles Coulomb established a fundamental law of electrical force between two stationary particles. And what he said basically was, as you know, the basic rule of electricity, like charges repel one another, and unlike charges attract one another. And this force of attraction is directly proportional to the magnitude of two charges. You see this, the magnitude of the product of two charges, and inversely proportional to the square of the distance between those two charges. And I want you to notice that this looks very much like Newton's law of gravitation. So here's what Coulomb's law basically says. It says that an electrical force has the following properties. Number one is this force is directed along a line joining these two particles and is inversely proportional to the square of the separation distance between them. So very much like our law of gravitation. So if you remember, it says it's directly proportional to the product of two charges and inversely proportional to the square of the distance between them. And the second property, of course, is the force is proportional to the magnitude of the products of the charges. And it says also that if the charges had the opposite sign, then it is attractive, and if the two charges have the same sign, then it's going to be a repulsive force. So the magnitude of this force is directly proportional to the product between the two charges and inversely proportional to the square of the distance between the two charges. So Q1 and Q2 are the two charges, and R is the separation distance between the two charges, and K is a constant we know as Coulomb's constant, and is actually 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. Now you'll notice that the meters squared will be canceled by the distance squared, and the Coulomb squared will be canceled by the two charges, and the sign of the charges really doesn't make a big difference in the answer. It's just going to tell us whether it's going to be an attractive force or repulsive force. And one other thing that's important to remember is that Coulomb's law applies only to point charges and only to a spherical distribution of charges, in which R is going to be the distance between those two charges. And just to bring you up to speed, the charge of an electron, we're going to have as E is 1.6 times 10 to the minus 19 coulombs, and that's going to be negative, and the charge of a proton is going to be positive 1.6 times 10 to the minus 19 coulombs. Okay, when using this equation, I want you to only substitute the charge's magnitude without sign, okay? You don't have to put positive and negative for Q1 and Q2, as I mentioned in the prior slide. Don't substitute the negative numbers for these symbols, and this is because the equation only gives you the magnitude of the electrical force, and the magnitude of a force cannot be negative, okay? So that's what we're looking for, is the magnitude of the force. And one other thing is K is very often written, in a different way. It's written as 1 over 4 pi epsilon O. You're going to see it written like that very often. And this epsilon O right here, is what we call the permittivity of free space. And it has a value that is given according to epsilon is 1 over 4 pi 4 pi k, and that equals 8.85 times 10 to the minus 12 Coulomb squared per Newton meter squared. Okay, and again, this is not really that important to know, but I want you to be familiar. Very often you're going to see K written as this 1 over 4 pi. We say 1 over 4 pi EO. So let's give it a go. Let's try a problem. In our first problem, we have two objects that are 1 Coulomb and -1 Coulomb, and they're separated by a distance of 1 kilometer. And compared to that big distance, these charges are going to be very, very small, or the size of the object. So what we want to do is find the attractive force that either charge exerts on the other. So we're going to start with our formula, F. Let's get the pencil in there. F equals K Q1 Q2 over R squared. Always start off with our formula, and then let's substitute in our values. So K, if you remember, we're just going to round up. We have 8.99 times 10 to the 9th. We can just round up to 9 times 10 to the 9th. Newton meter squared per Coulomb squared. Again, it's not necessary to put in the units if you don't feel like it. Okay, so we're going to start off with K is 9 times 10 to the 9th times 1 Coulomb. Okay, and then we're going to multiply by the other charge, which is also 1 Coulomb. Okay, remember, sign doesn't matter, over the distance between them, which is 1 kilometer, but we can't use that, so we're going to have 1.0 times 10 to the 3rd meters. And remember that we have to square that. So, plug this into your calculator. You have 9 times 10 to the 9th times 1 Coulomb times 1 Coulomb divided by 1 times 10 to the 3rd coulombs. And if you calculate correctly, you should come up with 9.0 times 10 to the 3rd newtons. And that should be your answer. And the force that you calculated here, obviously we would have +1 and -1 would mean that would be attractive, but this corresponds to about 2,000 pounds, and it's really, really large because the charge of 1 Coulomb is enormous, and such big charges like this are pretty rare and encountered in the most severe conditions, maybe like in a lightning bolt where as much as 25 coulombs could be transferred between a cloud and the ground. Now, typical charges produced in a laboratory are much smaller and are measured in microcoulombs. Remember, 1 microcoulomb, let's see, 1 microcoulomb is equal to the 10 to the minus 6 coulombs. So that's typically what we're going to be using. So as mentioned earlier, the Coulomb's law, K, Q1, Q2 over R squared, where you have two charges, is very similar to the law of gravitation. We're going to put this as E for the electrostatic force, and the gravitational force, if you remember, is G times M1, M2 over R squared. Now, this is gravitation. A big difference is that K, remember, is 9 times 10 to the 9th Newton meters squared per Coulomb squared, which is, this 10 to the 9th is very, very large compared to G. G, 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. So they're both similar in that they're both inverse square laws, and they're both proportional to the product of something, but they're different because, number one, is the Coulomb force is so much stronger, the electrostatic force so much stronger than that gravitational force. So before we quit with this lesson, let's take two more examples. One, let's contrast the magnitude of the gravitational force to that of the electrostatic force. And we'll start with the electrostatic force. Let's go to the pencil. There we go. So F equals K Q1 Q2 over R squared. And we're going to plug in the values. Okay, 9 times 10 to, this is K, 10 to the 9th, I'm leaving the units out. And the charge of a proton, you remember, is charge of a proton is 1 point, hello, back to the pencil, 1.6 times 10 to the minus 19 coulombs. And the charge of an electron is the same, so we're just going to square that because they have the same magnitude. And we're going to say that these charges are going to be separated by the distance from the nucleus to the proton, which is about, I'm just going to give you this number here, 5.3 times 10 to the minus 11 meters. And we're going to square that. Don't forget to square it. That's the most important part. Lots of people forget to do that. Okay, so carry this out on your calculator. 9 times 10 to the 9th times 1.6 times 10 to the minus 19 coulombs squared. Again, the reason we did that, the proton and the electron have the same magnitude of charge. And we're going to divide that by the distance between the proton and the electron, which is 5.3 times 10 to the minus 11. And I'm going to give you a second to calculate. And you should come up with something along the line of 8.2 times 10 to the minus 8 newtons. And that is going to be the electrostatic force between the proton in the nucleus and the electron. Now, I want you to do these along with me just to check and make sure your order of operations is working out on your calculator. So now, let's do a force between the proton and the electron, the gravitational force. I'm going to go to the next slide. By the way, just as a matter of information, these constants will be given to you like the mass of an electron, the charge of an electron, and the mass of a proton. So, and also gravitational constant and the electrostatic constant. So G, if you remember, if not, just look it up on your AP information guide. It's 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Okay, that's G. And the mass of a proton and the mass of an electron are very different. Let's see the mass of an electron. It's 9.11 times 10 to the minus 31 kilograms. Very small, very, very small compared to that of a proton, which is 1.67 times 10 to the minus 27 kilograms. Again, that information will be provided for you. And their separation distance, still the same separation distance, 5.3 times 10 to the minus 11 meters. And we're going to square that. And what I would like for you to do at this point is just to pause and calculate on your calculator to see what you get. And if everything went well for you, you should get something along the order of 3.6 times 10 to the minus 47 newtons. That's the gravitational force. And compared to the electrostatic force, which we said was 8.2 times 10 to the minus 8 newtons. So let's do a little ratio here. Let's say the electrostatic force to the gravitational force. And we set that up. Go ahead and calculate that. And you should come up with about 2.3 times 10 to the 39th. The order of magnitude of 10 to the 39, that's enormous. So I think you have a good idea of how to do the basics with this. Coulomb's force is so similar to that of the gravitational force. So we're going to stop here, and then on the next little short lesson, I'm going to do charges in a plane. So thank you very much.